Yeah, Françoise was very kind, and she has given me half an hour of her talk so that I can complete what I had no time 2 days ago about talking about the relationship between magnetic space groups and irreducible representations. I'm afraid I will again be very slow, so probably I will not have again time, but I think it's better to go slow and to get very clear messages instead of speeding up to try to put all the stuff at the same time. So, as a summary of what I tried to say yesterday, you have it here. I mean, one case historically, and you have seen it even in this course, in this workshop, that people just treat the two things as separate things. I mean, I'm going to use irreducible representations, I'm going to use magnetic space groups. And my message is completely different. I mean, you should not do that. I mean, as a method, okay, you can start with reducible representations, you can start with magnetic space groups, but in the end, they are completely different things. And to characterize your magnetic structure, you have to arrive to know what is its symmetry group. That means its magnetic space group if it's commensurate, and its superspace group if it's incommensurate. Whatever method you have used to determine your structure. I mean, that's my opinion. That's what in these guidelines that have been mentioned several times, it is said by the Commission on Magnetic Structures, where many of the experts are included there as co-authors and are co-signing these guidelines. So this was the point, the historic point that they have considered, and it is, as I said, up to now, it is being used as alternative methods, as you have seen, for instance, in the first talk of this morning. As I showed you yesterday or 2 days ago, Juan and myself, we tried to make the point that this should be changed, and now this strain relation and separate relation of the two concepts should be finished, and they should be used together, combined. So because the best approach is to combine both concepts, and you have now computer tools available that can make very easily and direct this combination of the two concepts. And now, again, the last day, what I started to show you is that there are two main situations that you are going to find in your magnetic structure. The most probable one is the situation which is indicated here, that I call it case 1, where your magnetic space group, I'm talking about commensurate structures, just to simplify the thing. If you have a commensurate structure, there may happen two situations. One, which I call case 1, that the magnetic space group is compatible with only one single irreducible representation. And as I put here, about 70% of the published commensurate structures enter in this situation, that you have, if you go to the magnetic space group of this structure, this magnetic space group only allows a single irrep, or the other way around. I mean, if you go from the point of view of the irrep, you will finish, and this is the difference, you will not finish with a single magnetic space group when the irreducible representation is more than one-dimensional, it's two-dimensional, three-dimensional. You will have several possible magnetic space groups for a single irreducible representation. So there is no one-to-one correspondence between the two concepts. And then the case 2, which is more complicated, and which you have more, once you know the magnetic space group of your structure, this magnetic space group can be or is compatible with more than one irreducible representations. And in this case, there is where the application, the combination of the two concepts is much more important, because it means that your magnetic space group does only constrain the degrees of freedom of your spin arrangement within a space where not only a single irrep is possible, but several ones. And in this case, you can apply basis vectors, basis modes, just to separate the contributions of different irreps. So let me just remind you what we did the last time. We were just showing this example of case one, so the simple and most probable situation, where you have a parent paramagnetic structure, you have your wave vector that you have determined, or propagation vector that you have determined experimentally, and you want to know what possible magnetic structures are compatible with this information. And we started only just by using the concept of magnetic space groups. And I told you that maximal subgroups are the most probable ones, and in fact, for this particular case, this is the one that is realized. When your magnetic structure, your magnetic space group is a maximal subgroup, you can be sure that your case is case one. I mean, there will not be any other irrep which is compatible with this symmetry. And I show you that the Bilbao server has a very nice option that you can click, and then instead of seeing this list of possible symmetries, you see only this one, which is much less, and that only gives you the symmetries, the magnetic space groups that correspond to a single irreducible representation. Of course, you can do something, and well, only for notation, for nomenclature. What we have here is that all these, well, I think I will leave this for that once you have a single irrep involved in your let's say instability or your primary magnetic ordering, it is a mathematical problem. You have put here your matrices of your irrep, and depending on what we call the order parameter direction, you have several possible magnetic space groups for the same irrep. And we call epikernels the ones which are special directions, that symmetries for special directions, and we call kernel of the irrep the symmetry which corresponds to a very general direction. I mean, an arbitrary one and in general, in the isotropy software, all of them are called isotropy subgroups, okay? Only just that you know the slang that we use to name all this stuff. And I show you also in the output of K-Mag that you can go to this click here, and it gives you a very important information. It tells you that this symmetry, that it has been listed without no knowledge about irreps. We are only using symmetry and saying what symmetries are compatible with my information of the wave vector, the propagation vector, and the parent group. Then it gives you information about the irreps. It tells you here that this is the group that I have chosen. It tells you that this corresponds to this irrep here, but for a special direction AA, okay? So this is what we call the primary rep, or the primary order parameter, that it is just giving you a distortion or a magnetic ordering according to this magnetic space group. And as you see in this list, no other irrep with an M, it means there is no other magnetic irrep that is compatible with this symmetry. with the symmetry that you have put in the input. So it means it belongs to case 1, okay, the simplest and most frequent case. But the K-subgroups MAG has also a very nice filter here, which corresponds to the other approach. I mean, if you don't go to the big list of all the magnetic space groups, but you just, from the very beginning, you say, no, I want to just concentrate in a single rep and see what happens, or what are the possible symmetries. And that's what Jana does, that was shown yesterday. Just, it lists the possible reps, and then goes, and then you can choose one, and for this one, it gives you the epikernels and the kernel corresponding to this rep. And it is also what it does isodistort in the method 2. In the method 2, you enter a parent structure, and then you choose a k-vector, then for the k-vector, you choose the rep, and the program gives you the possible magnetic space groups for this rep. And then it constructs an MC file, or you can construct an MC file, see it visually, and so on, in the same way that the only difference between Jana and isodistort is that isodistort can do it for several k-vectors at the same time, which Jana cannot do it, and Jana has the advantage that you can go directly to the refinement, while isodistort, it only just produces files that you can translate, you have to transport to your refinement program. So, and this we can do also with K-subgroups MAG. You go to the filter here, you choose your irrep here, and then for this irrep, it only lists 3 possible symmetries. So you go directly to the symmetries that correspond to this particular irrep. So this will be exactly what you would obtain also in isodistort or in Jana. And when you compare it with what we had before, we had these 3 symmetries corresponds to one of the reps, and these other 3 symmetries to this other one. And the point now is to realize that when you make a model with this magnetic space group, and you compare it with what you would do, for instance, using only saying, okay, I use all the basis vectors that come from Sara or come from basis reps, you will have 6 basis vectors, that means 6 amplitudes to refine, while here, when you are here, you have only 3 parameters, 3 degrees of freedom. Why? Because of this situation here, that you have to choose a very special linear relation between the basis vectors. So they have to be combined in a particular way that you don't know exactly, because this is a very abstract mathematical way to describe it, but you know it is, you have to combine them. And it means the number of degrees of freedom decreases from 6 to 3 automatically. And now you are restricting your symmetry not to this symmetry here, but to this symmetry here. And the difference between this is very important physically. In this case, you have a point group which is polar, and is indicating that it's going to be polar, a polar system along one of the orthorhombic axes. And here, it is a centrosymmetric point group and a centrosymmetric space group, which does not allow polarization. So if it is here, it means your system will be multiferroic, in the sense that it allows, as a secondary effect, some polarization. And this is the result. I mean, if you just construct your MC file with either Jana or with the isodistort or with K-subgroups MAG, you will produce an MC file that you can go to the refinement, and in the end, the refinement will have 3 parameters which are very physical. They are just the components of the of a single magnetic atom, which is the one which is symmetry independent for this particular magnetic space group. You do not have to worry about basis vectors, basis modes, whatever. Just the basis mode is included in the symmetry operations of the magnetic space group. It is taking care for everything. So you don't have to use basis vectors at all. But you are doing a model according to a single irreducible representation that you have chosen. And with the particular property that you have chosen this irreducible representation, but in a particular direction, so it means a particular magnetic space group. And then we finish here, more or less. The case 2, the more complicated one. I have this example here, which is the one which is considered in the guidelines in this report, which is called the Guidelines of the Commission. And this will be the starting point, the parent phase, paramagnetic phase, an hexagonal paramagnetic phase. You have the manganese in a special position. And now, if we do exactly as we did before, there is a big change, or an important, very important change, that again, we list the possible magnetic space groups that can result of a single irreducible representation. That means only using basis vectors corresponding to a single irreducible representation, and this is the result. And it means now we have something that if we do the same thing that we did with the first case, we could see that all these possible symmetries correspond to one-dimensional IREPs. You remember that it was stressed several times that there is a one-to-one correspondence if the irreducible IREP is one-dimensional. And all these irreducible IREPs are one-dimensional. So whatever program you use, when you go, just give me the magnetic space group corresponding to this IREP, it will give you this one, and nothing else. There is no, so this is the most simple case, one-to-one, okay. But this is the complication comes, and what is important is that the non-equivalence between the two approaches is because if you just take this other rep, which is two-dimensional, for instance, then it gives you, again, as in the previous case 1, it gives you 3 possible symmetries, the epikernels and the kernel. Okay. Now, all these symmetries are possible according to the output of the program for a single IREP. And this identification, which corresponds to which IREP, I did it just using the same program, get MEREPs, okay? The one that, the output I show you here, you can do it for any of these just by clicking here. For instance, for this one, I click here, and what I obtain that this and this are just, and here the fact that I see only an A, it means that this IREP is one-dimensional, okay? And then I know that there is a one-to-one correspondence here. I don't see any M IREP, magnetic IREP, except this one, so it means this is case 1. Case 1, and even more simple than the one that I put as an example before. But if I go to this group here, and I do the same thing, what I obtain is a list of 2 IREPs, okay? This is, I call it the primary IREP. Why? I can identify it as a primary IREP because immediately I see that the symmetry that comes out for this particular IREP is exactly the one that I put as an input as for the symmetry break. So this is the primary IREP, and this one, it corresponds to a different symmetry. and necessarily then it is a secondary rep. Why this one appears here? It's because of a very simple reason. Because this group is not maximal. And as this group is not a maximal subgroup of this one, there is an intermediate symmetry here, which is exactly the one that appears here. Okay? That means, remember the talk of Dimitri some days ago? It just made the stress that in general you have primary order parameters and secondary order parameters that necessarily I couple with the primary ones. And this group is telling me that there is a secondary degree of freedom which corresponds to this possibility of a coupling with this secondary order parameter, which has a completely different symmetry properties, which are given by this irrep, which is one-dimensional. And here you see that, again, the direction is special. It is not AB, it is A and A multiplied by something or divided by something. It means you have to take a special direction to arrive to this thing. So it means, again, I could use the program, I could use YANA, or I could use IsoDistort, I could use our program with the filter of an irrep. I filter saying, give me the symmetries for this particular symmetry, and I will obtain only this list, and I obtain the list, and I made the graph, but you obtain, of course, the list also. And in this list, you see, if you go to the decomposition of the magnetic representation according to irreps, here you have the M gamma 6 plus, okay? And I want you to, I think it is very important that you are able, without knowing still your magnetic structure, if you are making a model, just to know how many degrees of freedom is going to have your model, okay? So only from this equation here that you can obtain with bus reps, with the, or with our program, this magnetic rep, you must know how many parameters you are going to have corresponding, or how many basis vectors. Here it's saying this irrep is, the multiplicity is 2, it's twice in the magnetic representation, and it is two-dimensional, okay? So it means that I have 4 degrees of freedom. Basic reps will give me 4 basis vectors of 4 basis functions for the refinement. If I say I want a refinement according to this irrep, you will have 4 parameters to refine. And you will be here in this symmetry, okay? If you want to go into this special direction, you will have to use a combination of magnetic space groups and just go to the symmetry that can give you IsoDistort, our program, or YANA. In the sense, it's going to tell you for this irrep, there are 2 possible magnetic space groups, which are the epikernels of highest symmetry, and 1 of lowest symmetry, which is the kernel. And you can choose one or the other and make the refinement in one of these 2 here. And again, physically they are rather different. Probably in powder diffraction you will not be able to distinguish the 2, and you will have to say, okay, it is one or the other. But you see here, this direction here for C, as it is not primed, it's ferromagnetic. I mean, this symmetry will allow weak ferromagnetism along this direction, and this direction, it's this direction here. While in this case, the ferromagnetic direction is here, and this direction is B. It means that, for instance, in the same way that I show you in another system, you could apply a magnetic field that will couple with this weak ferromagnetic component and just by rotating the sample, if it's a monocrystal, of course, then you will be able to switch the arrangement from this symmetry to this symmetry, because the ferromagnetic component will force the arrangement to rotate accordingly and to be always aligned with the magnetic field. So, but the point is that we said there is a supergroup here, intermediate, and according to the von Neumann principle, everything that is allowed by symmetry will be present. That was also the stress of Dimitri, and this is what we have it here. That means that apart from these two parameters that corresponds to the gamma 6 plus, but restricted to a particular direction, you have another degree of freedom, or many, maybe more, corresponding to this irreducible representation gamma 3 plus. And you know how many degrees of freedom you will have just by looking again to this decomposition. You have only one time m gamma 3 plus, and it is only one dimensional. So it means it's a single parameter additional that will be in the model. So in total, considering this and this, you must have 3 parameters to consider. And this is if you construct your MC file, either with isodistort or Jana starts the refinement, it will start the refinement just with a model that it is summarized here in an MC file that can be constructed or has been constructed with K-subgroups MAC combined with MVisualize, which is the other program that you have to use, combined with K-subgroups MAC. And you see here there are the 3 parameters which are free in the refinement, MX and MY for this magnetic manganese and My for this other one. The symmetry has split the manganese into 2 symmetry-independent manganese, and now you have 3 parameters because this is the restriction that comes from the magnetic space group. The result is, in fact, that you can start your refinement with the 3 free parameters, and you will see most probably that the system likes to put them equal modulus, and this one with minus sign. So in the end, you finish with a single parameter, when in fact, even if the irrep is restricted to m gamma 3 plus, m gamma 6 plus, I'm sorry, then it will be 2 parameters. So, and this is the weakness and the strength of using magnetic space groups and magnetic symmetry groups in general with superspace. It gives you, and they are entangled all the degrees of freedom which are allowed, okay? Not only the ones of the irrep that I have chosen as the one corresponding to the order parameter, but also the degrees of freedom corresponding to these possible secondary modes. It is the strength because then you know what can happen, okay? What is allowed in this phase. And it is the weakness because it gives you all the degrees of freedom with the same, without any hierarchy. You don't know which ones are more important than which ones, okay? They are the 2, we said there are 2 degrees of freedom, some corresponding to what we call primary and one corresponding to a secondary one. But when we refine in this way, they are mixed here. I mean, you cannot, so this is the point, this is the result that at the end you will obtain for the 2 possibilities. This, I already made the point that you can use these 2 programs to determine these epikernels and kernel of any rep. as we do also in the Bilbao server. And now I want to say that you have, I put it here, this is the future and it is already available. So this is my recommendation, my opinion, this is the best way to approach any commensurate structure, to use both concepts at the same time. And the only possibility to do that is using ISO-distort. There is no other program, unfortunately the Bilbao server also not, that can do that. That means you just start with your irreducible representation, then you calculate the epikernels and kernel according to ISO-distort. You choose one of these, of course you must try first the epikernels before going to lowest symmetry, so you try the epikernels first, and here and ISO-distort is going to, in method 2, from ISO-distort method 2, you have, there you choose your irrep, then you choose your particular magnetic space group, and then, as Branton showed, there is a point where it says PCR or something like this, and you click there, and the result will be a PCR file where you have the asymmetric unit, and you see all our zeros here. You are not going to refine the positions of the magnetic all the atoms of the structure. In principle, you could, of course, refine them also if you think you have enough good data, but in most cases you cannot do it. So you fix all the positions, and here it gives you a list which defines what we call modes or basis vectors or whatever you want. I like them to call them modes. From the traditional way, they call them basis vectors. But the difference with the basis vectors that you are used to see in BASIREPs or in SARA is that here they are defined only in the asymmetric unit of the magnetic space group. So you don't need to just make the full orbit, this is plus, minus, pum, 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 and make a full table of how is the basis vector. You just only have to define the mode by defining some correlation between the magnetic atoms, which in principle, according to the symmetry group, they are independent, but according to this mode, they will be correlated, okay? And this is one, and well, I have and here, the refinement of each of these modes will be here. The number here means that these two lines corresponds to the same mode, these two lines correspond to the same mode, and so on and so on. So let me just show it a little bit more, explain it. This is one mode and corresponds to the gamma 3 because it's indicated here, gamma 3 plus, okay? This is a second mode, and now it's gamma 6 plus, and this is the second mode for gamma 6 plus. You remember that gamma 6 plus was contained, the multiplicity was 2, so I must have two modes of gamma 6 plus. And these are the ones, this is the normalization that comes out from ISO-distort, and Juan explained how you can just put in the PCR just to make it that these amplitudes that are refined are exactly in Bohr magnetons, okay? But let me just explain that what is saying this, for instance, is only that you have to move, or you have to have the component of the spin 1 and 2 related in this way. This one does not move. The second, I'm talking move because I'm thinking of displacements, but it's the same as with the spins. I mean, you have only a spin in the one and 0 in this one, and here you have this correlation that the component is twice and opposite value or opposite terms like here. And this has the, now that you have this, you can play. I mean, you can say, okay, I don't want this mode, I just want a refinement with this gamma 3 plus 0. And I don't refinement. refine it. So I make a model only with the primary IREP refine. And then if it works, okay, let's see if there is some kind of small coupling with another, with this secondary degree of freedom, and you can control this possibility in a perfect way. If you do it, the isodistort and foolproof can even do it, and Juan showed it in a very complicated case where you can also include modes for the distortion, that means for the displacement. And you can see, and you, in a very controlled way, see if there are some kind of magnetostructural induced effects in your structure. In most cases, magnetostructural effects are very weak, but the point is that in most cases, they have been investigated with no control. I mean, you didn't know what kind of degrees of freedom in the structure can be induced, and the way to do it is in this way, because in this way, you know what is allowed by coupling and what is not allowed, because the magnetic space group is the one that tells you what can be allowed both in the positional structure, in the positions of the atoms, and in the spins. What is the result of the refinement if you do it like this? Of course, in the original paper, it was not done like this. It was done, I think, even not using magnetic space groups, only Basi reps probably, or irreducible representations. But the point is, if you do it like this, the result is going to be more or less like that, okay? These two will be equal, because when these amplitudes of these two modes are equal, then you finish in this type of mode, which is the one that you observe in the final structure. And if you combine them instead of with plus, with minus, then you arrive to this other mode, which is still gamma 6 plus, and which is the one that the amplitude is 0. And why the system likes this one? Because this is the weak, I told you that the system allows weak ferromagnetism. This is the mode that corresponds to the weak ferromagnetism, and which is, in most of the cases, you cannot see it with neutrons, but it is there. I mean, if you make normally a macroscopic measurement, you will see this small, which is normally 1 order of magnitude or 2 orders of magnitude smaller than the magnetic modes in the other case. Unfortunately, the output of isodistort does not count this, so it gives you two basis modes that are not mathematical obtained, so it does not say, okay, this is a ferromagnetic mode, so let's combine the two basis modes in a different way so that I obtain a ferromagnetic mode and the rest, which will be the logical thing to do from the very beginning, okay? Because the basis modes, there is a degree of freedom in the choice. I mean, you can then combine them, and as long as they are orthogonal, you can change the basis in the way you like. And this is the form that probably, if you want to complete the description, this is the description only using magnetic space group. If you want to complete the description saying this magnetic structure includes the possibility of secondary modes, and the magnetic IREP has two modes available, one with amplitude 3, which will be this one, and the other one with amplitude 0, according to the final model. And the next one, also with amplitude 0. So that's, what about incommensurate structure? So it's, any question about what I said up to now? Everything is clear? So the answer is incommensurate structures. What is, well, I have to make propaganda again of a paper, okay? So it's which was written long ago in 2012 with Vaclav is here as co-author. So we worked together just to make a review of how you describe magnetic structures with incommensurate with superspace groups. And again, the principle is the same. You start with your parent phase in your parent space group, gray group, if you consider magnetism, and you have possible reps, and the possible reps you have the epikernels. Margarita showed yesterday how Jana can do it, and so on. And the only thing I want to stress is that in this paper, it is said very clearly that for two-dimensional reps, there is again a one-to-one correspondence between the rep and the magnetic superspace group. In the commensurate cases, you remember there is a one-to-one correspondence if your rep is one-dimensional. In the incommensurate cases, there is a one-to-one correspondence if your rep is two-dimensional. What happens if it's one-dimensional? Well, the answer is there is no rep incommensurate that it's one-dimensional. You have the k and minus k always. So it's always, and if the k is incommensurate, they cannot be equivalent. And therefore, by definition, the rep is two-dimensional as minimal. Well, it seems that that Vaclav just cosigned, he forgot it. And so, in fact, as Margarita showed, it shows also for a two-dimensional rep two possibilities. This symmetry that I showed here, and another one lowering the symmetry and losing the inversion center. And and this happens also with isodistort. You have these two possibilities, and here it says for a very special direction A0, and this is not true. This is very misleading. This is for any direction of your order parameter. There are no epikernels in the case of a two-dimensional incommensurate rep. This other one, you see, in the end, it has an asterisk. And you have to read this long sentence to indicate what it means. It's not very clear, but what it means is that if you are using this symmetry, in fact, you are using the combination or the superposition of two order parameters with the same rep, but phase shifted. And this phase shift, which is not allowed in principle in an order parameter, if you are in a single order parameter, these two modulations of the same symmetry, let's say, of the same rep, if you are there combined, they are just breaking the inversion center. But this means that you are getting out from the Landau approach, from the Landau hypothesis of a single order parameter. And this is, it can be misleading, and in fact is misleading in the sense that people, if they are not happy with this symmetry, they go to this one without realizing that this is a very strong statement saying, okay, this is not a solution for a single rep, it's a solution for the combination of two order parameters of the same rep. This happens only in incommensurate structures. In commensurate ones, you can combine two order parameters with A prime, B prime, and A, B, and nothing happens. The symmetry is not broken. But in superspace, symmetries, yes. There is also this situation of two possible epikernels for the same rep, which is in this case is four-dimensional. That's why you have two possibilities. If it were two-dimensional, I said there is a one-to-one correspondence, and so you can obtain from a single rep a solution which is sinusoidal, a density wave, and another one which is helicoidal. And these two are seen in the diffraction diagram of the system. So the system, they compete, and you can see both of them competing in the phase diagram. Okay, so I think you can read the conclusions in the thing, but what I want to stress is please, 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 once you determine your structure by whatever method, you must identify the magnetic space group of your structure. Okay, so thank you for the moment. I think I'm going to stop here just to go to the next thing. Thank you. And maybe if there are questions, something about so how much time do I have left? 45 minutes, okay. So I've spent half of the allowed time, okay. So I have to talk about the MAGNDATA database and how to report properly a magnetic structure. So I will try to, I'm afraid I will have to speed up here because I took my time just to explain the other thing, which I think is very, very important. So let me go here, here again. Okay, so this you have it in the Bilbao server. I hope you had a look, all of you already, in the section of the Bilbao server. There are, at the moment, you see this slide is very old. It says 300 structures. At the moment, the database has about 2,200, about 150 incommensurate ones, and more than 2,000 commensurate ones. This was a project started a long time ago in the Bilbao server, but with a lot of collaboration of Koichi MoMA, because at the moment when we started, Vestat did not support MC files and magnetic structures in general. You had to do it manually and so on. And he was kind enough to, we pushed him to extend the program and to be able to support magnetic C files. And this was, I think, a big success. Now everybody uses this thing. Right? Then also Bob Hanson with JMOL that we use in the database, which also was in Bilbao and adapted the program for supporting magnetic C files and so on. You have two main papers where the database is explained when it was 400, only for about 400 entries. And, but most of the concepts are there, and I recommend you, if you are interested, to have a look, because, as again, I cannot explain everything that is in these papers. One is for the commensurate structures and the other one for the incommensurate ones. I also have to mention Emre Tachi, which is, who was a postdoc in Bilbao, and he's now in Ankara in Turkey, but he's still responsible of keeping all the problems of software, and he's responsible for the database. And the team in Bilbao, of course. So, as I said, there is two papers in Journal Applied Crystallography that I recommend you. And there is a tutorial also that it explains how you can work with the database to make searches, and there is very nice, for instance, if you want to see which structures are magnetoelectric, for instance, or which structures are have ferrotoroidic properties and things like that. You can do it quite easily. The structures are divided according to the K vector. So you have first the most frequent case, which is K equals 0, and there are more than 1,000 structures in this set. You have then 2 propagation vectors, 3 propagation vectors, and so on. You have a web page for making searches, which is very, very, I would say, powerful in the sense, for instance, to combine and to say, give me structures we have this tensor property or this other tensor property or both at the same time. So you can look for authors, you can look for elements, and also for if your primary rep is 2-dimensional or 1-dimensional and so on, you can make all kind of. If it's multiferroic, or it could be multiferroic if it is insulator. I don't know if it's insulator. The database does not specify if it's insulator or not, but it can give you the clue that it could be multiferroic of type 2. You can order the results of this search in very different ways, according to the date, according to the space group, so you can immediately look at a particular magnetic space group, if there are structures for this magnetic space group or not, according to the parent space group, and so on. You have a visualization tool using JMOL, and you can download the MC file. This is the most important thing. You can just download, and there are groups which have downloaded all the 2,000 MC files, and they have made massive searches and massive analysis of the whole set of structures, and we have no inconvenience that people do that. I mean, you can just make a script and just ask for the download of all the MC files. Of course, the server gets a little bit loaded, but you can do it. You can directly download a Vesta file just to show the structure in the way that we show them in the entries. I mean, they correspond to the figures that accompany any of the entries. And you can submit directly into an editor that can change, that you can use to edit the MC file and to produce a new MC file with different features. This is a picture of the JMOL visualization tool, where JMOL, I must say, it is terrible. It has thousands and thousands of commands that I think only Bob Hanson can deal with them. The document, the help document, is not very useful if you want to do it by yourself. So what we did is just a set of buttons of the things that are more frequent, or just to ease, to make user-friendly the visualization. But if you are an expert on JMOL, you can just click here and open a console here and put the command that you know, and then it is more flexible and you can do whatever you want. I mean, JMOL allows thousands of things. The important thing as I said, is that the ISODistort produces, it stores the entries as an MC file, and it gives you this MC file whenever you want. And this is a format that is supported by many of the programs, as you have seen in this workshop. As I said here, that's, I'm not going to go into this. I think we made a lot of stress on that. How is a zip file, that you define the magnetic space group, the unit cell, and the transformations to standard, if you are using a non-standard cell, and so on and so on. And this is the label of the group, and so on. The point is that once you go into one entry, like for instance this one, it doesn't work, okay, no problem. Then you have these buttons here allow you to connect directly with other programs of the Bilbao server. For instance, if you go here, you go to mTensor that I showed you in previous lectures, and there you can just investigate the tensor properties of this particular magnetic structure. You can just transform into the standard, if it's not in the standard, the description, and produce a new zip file with the standard description of the magnetic structure. You can change to whatever setting you want, and very important, you can change and go to equivalent descriptions which are domain related to the one that it is stored in the database. And it gives you also information. For instance, in this model here, you have a single parameter because this should be double of this one, but here is 0 according to the reported model. But according to the magnetic space group, it could have a MZ component. Remember, this could be a secondary irrep, but it could also be a degree of freedom that corresponds to the same irrep. And here there is, for instance, there are no secondary reps. There is only a primary one along a special direction. This is a very nice example where, because once you, how have we entered these entries in these structures in the database? This comes from this one paper that you can just see that it's the 125 in the database. And you see this figure in the database. Well, not this one, because this we constructed ourselves. And the paper said, in order to arrive to the solution to the proposed model, he had to, or they had to try 24 possible spin arrangements. It is straight indicated in the paper. We tried to 24, and this up to 24 possibilities. If you use what you have learned in this workshop, and you go to the maximal subgroups for this wave vector and for this site, then you get only 2 possibilities, okay? So you only have to try 2. And of course, I tried one of them on Pong. This is the one that they are reporting, okay? You have there, once you go to the historical weak ferromagnets that were reported many years ago, and you describe them and put them in the using magnetic space group, immediately you see, as I show in other examples, that the magnetic space group allows some ferromagnetism, which is this small component that we put here, which in fact, I think it was a mistake of us because this is not in the paper. This we added because there was, or even in, it could be in the paper, but as a macroscopic measurement, okay? So the Neutron experiment only gave this value for the component along X, but then they made macroscopic measurements, and they said, okay, there is indeed a weak ferromagnetism along Y. And as they gave up a value, well, we put it here, okay? But in fact, they come from 2 different experiments. And you see it is 2 orders of magnitude smaller. There are very nice structures in the database, multi-K structures like you see here. And I ask you to distinguish what is a multi-K structure, which are these ones, and you see here, you will see it indicated in the entries that this corresponds to 2 wave vectors, 2 propagation vectors, this to 3, and this to 3, and multi-axial structures, which are in fact single K. The fact that the spins are not in different directions does not mean that you need a multi-K model. There is something very interesting that most of the structures that are in the database are collinear. And, but in fact, the magnetic space group allows canting of this collinearity. So the collinearity is not symmetry protected, let's say. And when you go to the structures that have been determined with single crystal diffraction, in these cases, the canting are observed, you see less, let's say, collinear structures, okay? I just summarize here. Symmetry is often observed, especially with single crystal diffraction. Only 10% of strict collinear structures are not forced by symmetry. In the case of single crystal diffraction, you have only all the collinear structures, the 90% that are determined with single crystal, they are symmetry protected by the magnetic space group. Otherwise, you see this nice canting. For instance, it's related, I suppose, with the arrangement of the oxygens around and so on. Yes, and then you can have, for instance, this case here. This is an example of what I was saying. This is two entries of the database. One is collinear, okay? And both of them are in the same magnetic space group. And here, this is the output of the entry for the collinearity. And you see the magnetic space group is saying that My and Mz is allowed, and the model just has it 0. But then you go to another paper and look how it looks, completely different, right? And what is the difference? The difference is that these symmetry-allowed magnetic components are different from 0. There are conflicting models that are with different symmetries. In this case, it's much more different because the magnetic space group is completely different. And there are two publications with two different models. Which one is the correct one? The database does not guarantee that what is there is correct. I mean, we put the magnetic structure because it has been published, but nothing else. So you have to take into account this when you want to believe or not magnetic structure that is in the database. As I told you, there is a nice feature that this is the structure which is reported, and using this feature that I show you to go to domain-related configurations, you can go and construct this one here, and you see it is not obvious that they are just domain-related, because you change the sign of some of the spins, but not of all. So, for instance, these are change of sign, but these ones, they have the same sign. And this is not trivial. I mean, the relation between the two, in fact, is by the inversion center that has been lost, because the structure, the parent phase is, the magnetic space group is polar, and the parent phase not. There are structures which I myself doubt that they are correct, but as they have been published, they are there. This one, for instance, goes and it reports a weak ferromagnetism, but if you go to the symmetry group of this arrangement, it cannot have ferromagnetism because it's not allowed. It has -1 prime. It can have magnetoelectricity, but not ferromagnetism. And this one, for instance, claimed to be multiferroic, and again, from the symmetry, it is centrosymmetric, so cannot be. And a very important thing is, we said that magnetostructural effects are very weak, and how much time do I have yet? Sorry, how much time do I have left? 20 minutes. 20 minutes. Okay, so what so-called concomitant structural transition. This is when people report that when they see the magnetic ordering, they see a structural transition which just coincides in temperature with the magnetic ordering. And in many cases, they consider, okay, by some coincidence, I have a structural transition coinciding with my magnetic ordering. But in most cases, you can explain this structural distortion as a magnetostructural effect, because you go to the magnetic space group and you see that the distortion is just the one that you expect according to the symmetry lost, the symmetry break that you have. And a very nice example is this one of very famous chromium nitrogen. The database has two entries, one very old, 1960, which we included in the database long time ago in 2014. And we included a comment saying a PNMA distortion of the atomic positions is reported, but it was not specified. I mean, only the author said that the structure seems to have a PNMA distortion according to this space group. It says, the comment says not included here because the paper did not include this distortion, but the comment says the effective space group for atomic position is not PNMA, as assumed in the reference, but PMMN, okay? And this was said in 2014. And this you can calculate just by seeing to the OG label of the magnetic space group, because this gives you, the OG label is the symbol that you use for the magnetic space group using the Opekowski-Huchone setting. And this is this one, which is completely different from the PNMA. And in 2022, it was published a paper saying, okay, and they determined the distortion, and this distortion is in fact PMMN. So the comment is the structure has a strong structural orthorhombic distortion according to the space group PMMN. And I don't know if the authors read our comment, but probably not. I mean, it is just the fact that when you do you have good data and you have a structural analysis, then you arrive to the right. So it means that this structural distortion is an induced effect clearly. So incommensurate structures, I'm not going to talk, they are again classified according to the superspace magnetic space group. And more or less, there are MC files also standard for doing that. And I think I should, again, you have several possibilities. One is the one that the database has been used, as I said, in many massive studies. And the important point is how you can use the database, or what has been said already now, that when you solve a magnetic structure, please submit it to the database. And how you can do it, there are very clear structures here. If you click here, then you have a set of instructions, and then with just giving your email and your name, and then uploading a zip file with the PDF of your publication and an MC file of your structure, this is enough. And okay, so that's my first part, and now I have a few minutes to indicate how you do this submission. And Okay, how to properly report a magnetic structure? Not only submit in the database, but also in your paper in the publication. And there, what you have to go is read these guidelines that we have published about how the recommendations, how to report it. And here, I'm not going to make again the stress that what you have to do is just to use a crystallographic approach. Use the magnetic space group. You have to identify your magnetic space group and use the magnetic zip file to describe your structure. And the paper contains this example and with this table. And it reminds you what you have to do. Just put your parent phase, your propagation vector, the unit cell you are using with respect to the parent phase. So here, for instance, you are duplicating the C parameter, then the unit cell that you are using here, then the magnetic space group in symbols indicating the transformation to the standard if you are using a non-standard setting, which is in many cases the case. And here the list of operations that you can alternatively, I mean, I like it much more to use this, especially if it is in the text and not in the zip. In the zip file you have to use, of course, these ones. I mean, that's mandatory, but in the text or the paper, of course, you can use other formats, and this is a very simple one. So this is, you can read, the identification of is a must, as I said, and whatever. And then the positions of the magnetic atoms, of the non-magnetic atoms, and the magnetic moments for the non-magnetic atoms in the asymmetric unit. This is the very nice thing, that you just have to list only the asymmetric positions, the ones of the atoms which, for instance, isodistort, it says unique atoms. When you read list of unique atoms, means list of non-equivalent atoms in your unit cell, okay? The other ones are generated by the ones that you are listing using the operations of the space group. And that's it. And that's the nice thing I said, for the moments, you only have to list the ones of the asymmetric unit. The list of non-magnetic atoms, and here there is an explanation why you have to include the non-magnetic atoms. It's very important. In many cases, you determine the magnetic structure without any knowledge about the non-magnetic atoms, but in the end, to report the structure, you have to include at least approximately where the non-magnetic atoms are, because in fact, the magnetic space group and the properties depend not only of your magnetic atoms, they depend also of the non-magnetic ones. And nobody can do a proper analysis of your structure if only knows the positions and the moments of the magnetic atoms. They must know also the positions of the non-magnetic ones. In this case, is one case, this example is case one. Remember, case one, there is only a single irreducible representation, so adding information about what is the irreducible representation involved does not add any additional constraint, anything. You can get rid, and even if you have determined the structure using IREPs, in the end, the report is done with the magnetic space group, and this is enough. This is the case, as I show you. This is about the labels that you can use for IREPs. There are two notations that have been already mentioned. The one that is used by isodistort, by the Bilbao server, by fullprof, if you use the most recent approach, is reading the IREPs from isodistort and so on. If you use bus IREPs, for instance, in the old options, they, as Juan stressed, it is just an arbitrary numbering of the reps. So it makes no sense that I refine with gamma 3, and you don't list what it means, gamma 3. Nobody knows what is gamma 3, okay? Because it is an arbitrary label produced by the basic reps. So somebody, if wants to know what you are meaning, he will have to go to basic reps and produce exactly what you did, and so on and so on. So this, I think I made, is exactly the same that I talked in the previous lecture. And then this is the case that we said case 2, the example of case 2, okay? So this is exactly the same thing that we did for the other one, and this is the nice thing. You have the information exactly the same, and with 3 free parameters, and here you can add the information if you have it. If you don't have it, does not happen anything. The information about the structure is perfectly okay, it's complete, except that you are not decomposing into contributions of different basis vectors or reps that are allowed, and in this case you put the two, the secondary rep, the primary rep, and then you can list the modes and so on, as I showed you before. So this is something which I repeated already. And now, how to prepare an MC file for the database. You have the instructions in the Bilbao server, and I will distinguish 3 cases. Case 1, you have refined with FullProf, with Jesus2, with Diana, and so on. And then, immediately, these programs, after you have refined, if you have used FullProf using magnetic space groups, it will produce a magnetic zip file, and with this perfectly okay and perfectly useful, and so on. In case 2, the refinement program can provide you a maxi file, but as you have used a method that did not use magnetic space groups, then probably it can only produce a magnetic MC file, but in P1, in no symmetry. I think FullProf can do that. And case 3, you know your structure because you know how the spins are in a magnetic unit cell, but you have no idea what is the symmetry of that, okay? This is the 3 situations. Well, the first thing, in the case 1, you take your magnetic zip file coming from your refinement program, and you use the tool in the Bilbao server, which is mVisualize. You see it here, download complete MC file, and so on. So it means if you click here, once you have introduced your MC file, the JMOL will show you the structure and show you that it has been able to read it, and you see here your structure that it's okay. And then you click here, and the program produces a new MC file that gets rid of all crap that is in the MC file that is not needed for the entry in the MAGNDATA, okay? And it adds some things which are important for the database, which are the bibliographic information. I mean, which paper has been published with this structure, and so on. Then, case 2, you have a magnetic zip file of your structure, but in P1, okay? So, with no symmetry, with the whole list of all the atoms in the unit cell and the whole list of magnetic moments in the unit cell. Okay, what you can do is go to ISOCIF in the isotropy platform, and go to this program which is called ISOCIF, and it will read the zip file, and then there is an option which is detect higher symmetry. You go here, click, and the program practically works very nicely always. I haven't found any bug. So it tells you, okay, your structure has this symmetry, and I have changed the setting, so I changed the unit cell to produce it and to describe this structure in the standard setting of this magnetic space group. And this is very important because people just use this option sometimes and they do not realize that the output, if you don't do anything, is not in the same setting that you have introduced your structure, okay? And there are papers where they are completely, cannot be understood because they are incompatible. So this is the thing that you have to do. You have to go to the safe file of this new MC file that has been found by the program and click here, use alternate, possibly non-standard setting in C file. And here you have to include what is the transformation. And the transformation you have to include here is the inverse of this one here. And you have to do it by yourself. I mean, fortunately, the program does not tell you what matrix you have to put there in order to come back to your parent, to the setting that you were using. And the case 3. Case 3 is you know your structure, but you don't know its magnetic space group and so on. And there are two possibilities. You produce a P1 magnetic file, and the Bilbao server provides you with a template where you only have to list all the atoms here and all the moments here and do the same thing as in case 2. This will be a possibility. If the structure is very complex, it will take a lot of time just to this listing. And in my case, when I go to a paper and they just show a list of spins and so on, what I do is just to where we are, yeah, just go to our programs Maxman and KSubusMag, go to the parent phase, I mean introduce the parent phase, introduce the propagation vectors that are reported, go to the maximal subgroups or to the ones that are given here, and in practically 90% of the cases, immediately one of the cases corresponds to the one that is being reported. And therefore, then I construct the MC file with these things, and then you can introduce the information about the magnetic moments, but not the full list, only the ones of the asymmetric unit according to this symmetry. And I want to finish just by, if you have learned in this workshop, I think you must be able to do what I'm going to propose you, and as an exercise, and home exercise, okay? And this is a paper in Journal of Magnetism and Magnetic Materials from 2024. I mean, it has been published a few weeks ago. And you can see here the table of the how they are reporting the magnetic structure. Here is a table with the coordinates, parameters of the unit cell, and here is a figure, which is here, and here is the magnetic moment, the value, and so on. So now you should know enough with this information to construct an MC file and to submit it in the database. Because you don't need to submit a structure which you have published yourself. I mean, you can submit any structure which is published and which is not still in the database, okay? And this will be very helpful. And think you can learn a lot if you do it, because then if you are able to do that, you will be able to do it for your structure, okay? And, but let me show you something. This table here, the compound is the one that is listed here. I'm sorry I did not put, it's holmium, lutetium, iron, silicium, carbon. if you go to the list of atoms here, first of all, in no place it's the space group of the structure. You have to go to the text and go to some place to see what is the space group for this list of atoms. This, please, if you cannot report properly an ordinary structure, you will not be able to properly report a magnetic one. And this is an example how you should not do it. I mean, here it should be the space group, because otherwise you have to look at the text and see what they are referring. And another thing that happens is that when I went to the list of atoms, you see the formula has a carbon, and a carbon is nowhere. I wonder, what is happening? Well, the point is I had to go to the inorganic database and see if there are compounds of the same type. And the point is that the carbon is in a special position, and so they don't list it because it's in a special position 0, 1, half, 0, or whatever, so they don't list it in the table. And I went to the text and I said, okay, it must be here indicated somewhere. It's not indicated anywhere. So, so these errors, I think you should avoid when you report a magnetic structure. And please, the first one that just made the submission, it will be indicated. I mean, when there is a submission of a magnetic structure, there is a sentence in the MC file saying, submitted by such and such person. Okay? Thank you very much. By the way, I constructed a C file of the parent phase, let's say, of this structure. And it has been introduced in the material that you have available for the workshop from today on. So you have to look and to see the C file, because this is the starting point. You start with this C file, and then you construct this nice, very simple magnetic structure.